All right, so in this video, we're going to talk about the basics of our bimolecular nucleophilic substitution reactions, which we are going to call SN2 for short. S for the substitution, N for the nucleophile, and 2 for the bimolecular. We'll have a capital S, a capital N, but is a subscript, so it looks a little tiny, and then a normal number 2 to describe an SN2 reaction. Now, the overall reaction scheme is going to look the exact same for both SN1 and SN2, like we talked about in the last video. We're going to have a nucleophile. That nucleophile is going to react with a substrate. That substrate is going to include a leaving group, which we have listed here as L. Sometimes you'll also see me, instead of just saying L, I'll write it out as like LG for leaving group. Same thing. There's going to be a reaction that's going to form where this nucleophile is going to form a bond with your substrate and then kick out the leaving group. Now, in an SN2 reaction, this is a reaction that is concerted. And this idea of concerted means it happens all at once. So there are going to be both our components, our nucleophile and our substrate, which are going to be involved in our rate determining step. Now, from a mechanistic standpoint, what's going to happen is our nucleophile is going to be our source of our electrons. So we're going to start our arrow there. And it is going to come and it's going to attack the carbon that is connected to the leaving group. This carbon is going to be delta positive because this leaving group is going to be a delta negative. Leaving groups often have a good amount of electron density around them, which means when they leave and form this negative charge, that they're going to be a little bit more stable. So you're going to see things like halogens and things that are a little bit more electronegative. So this nucleophile is going to come and attack the carbon connected to the leaving group. That's going to be a delta positive carbon. And then in the exact same step, this bond, which is the electrons between our substrate and our leaving group, are going to head over towards the leaving group. This is a lot similar to like an acid-base reaction, where you can imagine your substrate almost being a hydrogen, and then the leaving group kind of being like our conjugate base component. So you have your nucleophile coming, attacking, and then breaking a bond. So you have a bond being formed and a bond being broken. This bond that's being formed, so this is kind of our new bond, is shown right here between our nucleophile and our leaving group. And then this bond that's being broken is being broken as a pair of electrons. So we have a lone pair that is going to be on the leaving group from the two electrons that were in the bond between our substrate and our leaving group. Now, we can describe this reaction in terms of kinetics, and we're going to talk a handful of times about what makes, of the different conditions that we can have, what makes this reaction happen faster. Because as we're doing reactions, we want it to be fast. We don't want to wait days for a reaction to happen. So we can write out an expression to describe the kinetics, or how quickly a reaction happens. And the kinetics for a SN2 is going to be related to the rate of the reaction. So the rate of the reaction is going to be equal to a rate constant. That rate constant, I saw lowercase k, just looks a little capital there, is related to a rate constant, and our concentration, which we're showing by the brackets, of our nucleophile and our substrate, which we're going to call like our leaving group. So both of these components are involved in our reaction, and that's why it is bimolecular. Now we can think a little bit about what these actually look like instead of like arbitrary nucleophiles and Rs, with some actual examples. So let's go and look at two examples here. Each of these examples have a hydroxide. So that is going to be an oxygen that has a connection to a hydrogen, 3 lone pairs. Oxygen likes 2 bonds, so it only has 1 right now, giving it a negative charge. That is going to serve as our nucleophile. We know that's going to be our nucleophile because of its negative charge. If it didn't have a negative charge, it could still be a nucleophile, but we'll be looking for electron density, specifically in the case of like lone pairs. Our substrate is going to be our other component. That's going to have a carbon, in this case a methyl or an ethyl on the second one, and then a chlorine. And that chlorine is going to serve as our leaving group. So that's going to be our kind of like our leaving group structure. Mechanistically, this is going to behave the exact same. I'll go ahead and do it in a different color in blue here. We're going to take one of the lone pairs and we're going to show a curved arrow from the lone pair to the carbon that is connected to the leaving group, and then the electrons that are in the bond between that carbon and that leaving group are going to be sent just to the leaving group. So you'll have a new bond that's being formed, which we kind of see over here on the products, highlighted now in blue, and then an extra leaving group an extra lone pair associated with the chlorine. Similarly, if we wanted to look at one that was kind of drawn out a little bit more in skeletal form, I'd again have my lone pair of my nucleophile come and attack the carbon that's connected to my leaving group, and then the electrons go to my leaving group. And you'll see that we're kind of just doing a substitution. We originally had an ethyl chloride, and now we have an ethyl alcohol. And all we did is just simply switch that chlorine and the alcohol. Compared to what we've learned in our radical chemistry when we're doing our bromination, this mechanism is a lot easier, and hopefully will be something that will get you a little bit excited about. Now, there is some important characteristics for our SN1 and SN2 reactions that are unique, and we're going to highlight each of those. For SN2, there is one term that is really, really common, and that is this idea of a backside attack. This is an inversion of stereochemistry. So we talked about the idea of stereochemistry back in chapter 5, where we're thinking about RNS configurations. In SN2, the stereochemistry is actually really important, and it actually changes. So when your group, your nucleophile, comes and attacks your substrate, it needs to attack from the opposite direction of your leaving group. If you have you almost think about this as like a one-way road. If you have your leaving group trying to go in a direction and then your nucleophile is trying to come in the same direction, they're going to kind of crash. They're going to be some steric interactions that are going to make that a unfavorable direction. So your nucleophile is going to come and it's going to hit the carbon in the back, and then kind of like almost like if you're like playing pool. You hit one of the balls and it hits into one and then bounces the other one off of it. Same kind of idea here. So you're going to have your nucleophile attack from the backside or the opposite direction of where your leaving group is. So then you can get the leaving group to leave without any issues with your sterics of like those two things kind of coming to the same location at the same time. Now with this, there is an inversion of your stereochemistry. So when you have your nucleophile coming in at this kind of like backside direction, you would now have all of your different groups all on the same side, and you wouldn't have that tetrahedral geometry. So what happens is all your other groups are going to be flipped over as that leaving group leaves. And you then therefore get the stereoisomer. So if something was an R, when you do an SN2, it's going to become an S. And you're going to get this kind of like flipping of an umbrella that they kind of show down here as at the bottom. And that's going to be a really important consideration that you're going to see in SN2. If we wanted to talk about a few examples, thinking about stereochemistry, here we have 3 different examples of substrates that have leaving groups, so chlorines and bromines. And we have 3 different nucleophiles. We have an iodine and we have some hydroxide groups. And we're going to think about what happens to the stereochemistry of each of these. So let's go ahead and start by just showing our mechanism. So we have a lone pair on that iodide, and that iodide is going to serve as a nucleophile. We know it's a nucleophile because it has a negative charge, meaning it has a bunch of electron density. It's going to come and it's going to attack from the backside or the opposite direction of where that bromine is, that leaving group, and then our leaving group is going to leave. Now, to draw this, you can either draw that completely inverted, like upside down, or what I do because it's a lot easier, draw that exact same general structure, except that bromine, which used to be a dash, is now going to be associated with a wedge. And then instead of having a bromine there, we did a substitution. So now we have an iodide. So the key thing is we've inverted our stereochemistry here. So if our original configuration was like an R or an S, we now have the opposite. So if it was R, it's now S. Now, a lot of times when you're thinking about SN2, you sometimes go a little bit quick and just flip all of the stereochemistry. However, the inversion of stereochemistry only occurs at the location of an attack. So here in the second example, you see that we have a wedge associated with a ethyl group, and then we have a chlorine. In terms of our attack, we'd have our lone pair on an oxygen, which is going to come, attack from the backside, and then kick out our chlorine. However, we'll notice that our stereochemistry is actually not at the location of where our attack is occurring. And that stereochemistry is not going to change. The only stereochemistry that's going to be changing is going to be the ones that are associated with the actual location where that chemistry is happening. So in this type of reaction, this stereochemistry will actually be retained because it's not where the reaction's happening, and we'll still have our OH being substituted out. In this original drawing, this carbon right here that was attacked is not a chiral center. There are two hydrogens there, so that is achiral. And here you remain achiral at that location. The wedged to a ethyl group there, that was not a location of where our attack occurred, so it does not change stereochemistry. And we wanted to tie those two ideas together. We can then see in this third example, if I have a 1, 2, 3, 4, 5, 6 carbon backbone and I have a chlorine and a methyl group, my nucleophile will come and attack at my leaving group from the backside, and then I'm going to kick out my leaving group. Same thing, all our mechanisms are that same general process. When I want to draw that product, I'll draw that same general backbone. At the location of the attack, which is this carbon here, I'm going to get an inversion of my stereochemistry. I used to have a wedge to a chlorine, and now I have a dash to my hydroxyl. However, my other group is going to stay the exact same because it was not at the location of the attack. So you don't just blindly turn all of your wedges to dashes or dashes to wedges. You're only going to change them at the location of attack. And that's actually kind of a cool technique that you'll sometimes see used by organic chemists to change your stereochemistry and get an interesting type of structure that you wouldn't be able to achieve otherwise. So that's kind of one of the big fundamental characteristics of SN2 reactions, this idea that there is an inversion of stereochemistry at our site of attack. Now, with attacking at the backside, there is another important thing that we need to consider, and that is going to be our actual substrate itself. I have here a graphic to think about the impact of our substrate. And here I have a series of different substrates. So we have a carbon that has a leaving group connected to it. And what we're going to do is we're going to change that carbon from a methyl to increase the amount of carbon stuff connected to it. So if I added a single other carbon in place of where there's hydrogen, we would call that a primary substrate because we have exactly one bonded carbon stuff. If I added 2, it'd be secondary, and then 3, it would be tertiary. 4 SN2 reactions would happen with this backside attack. You want your substrate to be very open. If you jump all the way down to kind of like this far right side where it's tertiary, there is a ton of steric hindrance from a bunch of those big bulky stuff. So in examples of like tertiary substrates, that's actually really hard to do a backside attack because you're trying to like push through a giant crowd in order to try to get to your actual substrate, that carbon that you're actually trying to attack. So for SN2s are really going to favor your methyl and your primary. And once you start adding sterics, your rate of your SN2 is going to decrease. You can do it on secondaries, but it will be a little bit slower. On tertiaries, it becomes really, really hard because of how much bulk there is. So for SN2s, you're going to get an inversion of configuration, and you really want unhindered or unsubstituted substrates. And there is one other final characteristic of SN2 reactions that is a little bit unique, and this is the idea of an intramolecular reaction. Now, most of the time, you don't see a bunch of intramolecular reactions, but it can happen. And SN2, it can occur if your substrate is actually big enough. So an intramolecular reaction is going to be a reaction that occurs within a single structure. So rather than having a separate nucleophile and then your substrate, you can have a substrate that has both a nucleophilic component and a leaving group component. So here is an example where you'll see that we have a bunch of carbons, and at one side I have an alcohol and at one side I have a bromine. If I react this with a base, and here I have an example of a base, sodium methoxide. If I react with this base, the most acidic proton is going to be the hydrogen on this alcohol. So I can remove that through an acid-base chemistry and get a substrate that looks like this. And now I have a really clear nucleophile and a really clear leaving group. And what can happen is this molecule can actually react with itself. So this lone pair can actually come around and then attack that carbon and then kick out that leaving group. And this is going to cause it to cyclize or form a ring. And this is actually going to make a structure that's going to look like this. So I have an oxygen, 1, 2, 3, 4 carbons. So I'm going to have a 5-membered ring. This is like a tetrahydrofuran-like structure that would be formed. And then you'd also get your Br minus, which would actually form a salt with the sodium. These intramoleculars are not super common, and you have to kind of control your conditions and concentrations enough to see it, but they can happen. And we'll look at a few other examples like in class of these. So if you see a structure that has both a nucleophilic component and a leaving group component with SN2, they can actually react in an intramolecular type style. So as kind of a quick wrap up or summary, our SN2 reactions are going to be these concerted reactions that happen all at the same time. We're going to have a nucleophile that's going to attack a substrate and kick out a leaving group. That's going to form a new bond between our nucleophile and our substrate, and then a lone pair that's going to appear on the leaving group as it's kicked out. These are going to happen in a relatively quick form. In order for this to occur, you're generally going to look for a substrate that doesn't have a bunch of sterics. That's going to be a little bit more of like a methyl or a primary substituted substrate. And there's going to be an interesting inversion of configuration. That's kind of some high-level capture of our SN2s. In class, we'll go through a bunch of examples of actually drawing a bunch of reactions and showing some mechanisms.